तो देखिए we were talking about temperature. Okay. Now we started with this thing that definition of temperature is a measure of hotness and coldness. But this hotness and coldness concept is subjective. It belongs to us. Okay? We say that thing is hot or cold by touching it. Now the thing is that body does not measure the temperature. That is what I told you. It measures temperature as well as the amount of heat. The duration of exposure. So the hotness depends upon how much is the temperature as well as how much the heat has transferred to the body. Okay, so that means it is not a true way of measuring the temperature. You cannot measure. There is no other way you can measure the temperature. Okay, so we have to find out some via media. So I gave you the example that even when two bodies are same, you have the two glass of water containing same temperature of water. One is that of steel and one that is of glass. What you will find that the steel one is hotter than a wooden or non-metallic glass, right? And simple, the reason being the body is sensing the effect on itself, because what is the objective of the body, or what is our objective of our nervous system? It is to protect ourselves, our body, from the any adverse situation. So body's objective is different and a scientist objective is different. He wants to measure the temperature, body wants to measure the thing, how much it is harmful to me. So these two are two different things, and that is why by touching you cannot give the sense of temperature. Okay. Then we talked about thermal equilibrium, and I said one thing, that heat flows in both the direction, from hot body to cold body and cold body to hot body. If somebody tells you that heat doesn't flow from low temperature to high temperature, then it is wrong. It flows either way. The only thing is the net heat flows from high temperature to low temperature. And there are certain cases in which net heat also flows from low temperature to high temperature. But that is that occurs in gas dynamics, right? And some part of that is in air conditioning. Okay. But that is actually a mix of, in gas dynamics, it's a mix of you can say the kinetic energy as well as heat. So it turns out that heat is flowing from low temperature to high temperature. But leave that aside, that you will discuss in I think it is in Rayleigh flow. You will be reading it next year. Gas dynamics, it is there. Okay. So what we say, that temperature, heat flows from high temperature to low temperature. Okay, that is the net heat flow. Now what are the temperature scales we have? There are 5 of them. You have Celsius scale. There is one is Celsius scale. The second is Fahrenheit. You have Kelvin scale, which is also called absolute temperature scale. Then Rankine scale. This is also called absolute temperature scale. And ideal gas temperature, it is also called absolute temperature scale. So these three are absolute temperature scale, and these two are a relative scale. Okay, so let us see what happens. So when you talk about Celsius or Fahrenheit, how does this scale work? It is called a 2-point scale. And you know the first point is ice point and the second is steam point. So what the scientists have done, they have said that the ice point, when the ice starts melting, let us call it 0. Let us call it 0. So they have themselves given it a value 0. Then take the steam point, when the water starts boiling, call it 100 degrees. Why do they do it? Because these temperature remains constant for long time. It is easy to produce 0 degree C and 100 degree C. But if you want to produce 50 degree C, you cannot. Okay. If you take any, if you keep water in a uh, flask and make it 50 degree C, okay, let us say whatever temperature is it, 50 degree C, we will call it 50 degree C. But you will not be able to maintain that temperature, because the moment you put water in the uh, uh, flask, it will start cooling down. Right? It is only when it comes to the atmospheric temperature, it will attain a stable temperature which you can measure. But atmosphere temperature changes day by day, time by time. So you don't know what the temperature is. But when you come to ice and water mixture, you can keep it at 0 degree C or a fixed temperature for a very long time. So long ice is there, it will remain at 0 degree C. Similarly, when you are boiling water and in a kettle or a flask, water is boiling and steam is forming, it is going out. So long the water is there, the temperature will be 100 degrees C, it will not change. So we have these two fixed temperature we can easily reproduce. Of course, these temperatures depend upon atmospheric pressure, right? When you talk about that water boils at 100 degrees C, it means the atmospheric pressure is 1 bar. Otherwise not. You must have heard it in your junior classes that water boils at 80 degrees C, 70 degrees C at mountains. It boils early because their pressure is low. So what is required is that you must maintain the atmospheric pressure at 1 bar for ice as well as for water, boiling of water. But it is easy to maintain 1 atmospheric pressure. You can have a big room and maintain the pressure as 1 atmospheric. You need not bother about what is pressure outside. In a laboratory, you can maintain that pressure of 1 atmosphere. Once you have maintained a pressure of 1 atmosphere, now if you take the distilled water, make it ice, put in a glass ice and water mixture, you will find that after some time the temperature will be 0 degree C and it will be fixed at that time. Similarly, if you start boiling water in a 1 atmospheric pressure, it will be 100 degrees C and it will maintain that. So these two are reproducible. That is why we use these temperature as a, you can say, governing points. They are the fixed points. Okay, so that is why these scales are called 2-point scales. Now, the problem is, okay, before that, there is some change which we did this. This was the initial thing. So as the people realized that there is something called triple point. It's called the triple point of water. Now the beauty of triple point of water is that if the water is pure, It is independent of the pressure. What is a triple point? When all the three phases of water are together present, right? So water is also present, ice is also present, steam is also present. If you can produce that, and people can produce that, then the temperature of that will be 0.01 degrees C. So what people did is, earlier they defined 0 degrees C as the ice point. Using the same scale, they found that triple point is 0.01 degrees C. So they didn't want to change their original scale. They didn't want to convert it to 0 degrees C. Now triple point be 0 degrees C. No, they said let the whole thing be same thing will be as 0 degrees C. But they have started using 0.01 degrees C, that is a triple point, as the reference point. So suppose they want to measure whether what is their scale is accurate or not, their temperature scale or thermometer is accurate or not. Instead of checking it from 0 degrees C, they will start checking it from 0.01 degrees C. Triple point. Okay, so now we have one triple point instead of ice point, and again the steam point. And why they adopted triple point? Because it's more accurate and independent of atmospheric pressure. Okay. So then we had this, and what they did is they used some. Now how do we measure the temperature in between? If I want to measure the 50 degrees C, how do we measure 50 degrees C? 70 degrees C, how do I measure? Okay, so what they did is, there has to be, so your temperature cannot be measured directly. This is the problem. By touching you cannot tell. How do you tell it? There must be some property observable connected to temperature. And what is that? You have some property, like you have a thermometer, you have a thread of mercury, and the elongation of the mercury tells you that what is the temperature. Okay. So they have to look for a substance, and that substance, if you should vary that property of the substance, let us take the volume of the gas. They are called gas thermometers, based on gas, ideal gas, or thermometer, mercury, or some alcohol. Okay, so you have to have some material whose expansion is measured, and that expansion is translated into temperature. This is what is happening. Okay, now the problem is, we assume that this expansion is linear. That means for each degree rise in temperature, expansion is same. But how do you know that? You don't know the temperature. So the problem is that you have to assume. So whether your substance is moving linearly or not, you don't know, because you do not know in between temperature. There is no way. So first you assume that your substance is moving linearly with the temperature, then with the help of that you measure the temperature. So again, your temperature is not accurate. It is dependent on something else, something which will, you can say, it depends on a particular substance. So then I should be saying that this is 50 degrees C as per mercury. This is 50 degrees C as per alcohol. This is 50 degrees C as per gas thermometer. But we don't do that. We just tell 50 degrees C. Now let us see what will be the problem, that if we, so since we do not know the temperature beforehand, it will not be possible to know the exact relation between observable property of the substance and temperature of the substance. Now this relation between the two we cannot maintain because we don't know the temperature beforehand. So we really do not know when the thermometer is showing 50 degrees C, it is actually 50 degrees C or not. We are calling it 50 degrees C. Okay. Now let us take an example. There are two different types of scales. Now this is your observable property on the x-axis. There is a property which you are measuring, and let us say it's the length or volume. Now on the other hand, there is a substance A which is changing like this by a temperature, and a substance B is changing following this curve with the temperature. Now what will happen when you are at L/2 and you say this is 0 degree C, this is 100 degree C, we can reproduce from ice point and steam point, no problem. But when we are at L/2, we call it 50 degree C. But when we are taking up A, it's actually 80 degree C. And we are talking about B, it is actually 15 degree C. It is only when it is linear. Only when it is linear, it is 50 degrees C. But how do you know it is linear? Because you don't know the temperature. How will you draw the relation? So the problem is, in measuring the temperature, you are assuming that your substance on the basis of which you are measuring the temperature is changing linearly with temperature. So this problem will always remain there. So that is with the thermometer, whether it is mercury thermometer, whether it is gas thermometer, or whether it is alcohol thermometer, it will always remain like that. Okay. But we have a way out. There is a way out, and we will talk about that. Then we talk about thermodynamic and absolute temperature scale. So what is the thermodynamic temperature scale? Thermodynamic temperature scale is one which is independent of the substance of thermometer. So we can develop a scale which is independent of the substance of thermometer, and that is called thermodynamic scale. How do we do it? That we will see later on. But there exists one scale. Okay, at least in principle it exists, and it is by virtue of second law. So when we'll be studying second law, then as per one of the corollaries of second law can prove that there exists a thermodynamic temperature scale which is independent of the substance. That can be proved from thermodynamics law 2, second law. Okay, but we will keep it to that point. But there is a scale. Then there is also a scale which is called absolute gas temperature scale, and that depends upon ideal gas. So if you have ideal gas, the scale you get, you call it is a absolute gas temperature scale. It is also called in a short form absolute temperature scale. Okay. Now this scale is also independent of the material, but you are using gas to find that temperature. There is no escape from this. You have to use some material. So use ideal gas and ideal gas is not available. There is no gas as ideal gas. Which one will be the ideal gas? Where the volume of the molecule is 0 and there is no intermolecular forces, but there is no such gas. And we know there are certain inert gas, and if you rarefy them, they behave closer to ideal gas. So you can approach ideal gas, but you cannot get ideal gas. Ideal gas is not available. But again, we have concept of ideal gas, and based on that we have certain relation, and we can prove that ideal gas temperature scale is same as thermodynamic temperature scale. That will also we will prove when we will define the thermodynamic temperature scale. So because thermodynamic temperature scale is independent of the substance, so ideal gas temperature scale is also independent of the substance. Are you getting the point? Actually, ideal gas temperature scale is working on ideal gas, and ideal gas is not available, so you will use a gas which is closer to the ideal gas, and then you will say it is independent of the material because it is same as thermodynamic temperature scale. There is no direct way for you to say that it is independent of the substance, because whatever substance you pick up, it has its own nature, its own properties, which will affect the measurement. Okay, so this is called absolute temperature scale, and this is equivalent to thermodynamic temperature scale, and we will talk about it later on. Now, Kelvin scale, Rankine scale, and ideal gas temperature scale are all thermodynamic temperature scale. They are all independent of any substance. Okay. Then one thing you remember, that for a Kelvin scale you will always use the letter K and not degree K. That is a standard notation, and we do not use degree K, we use K. Similarly, for Rankine scale, R is used instead of degree R, because both these scales are absolute temperature scale or thermodynamic temperature scale. So we are not using degree here. Remember, and with Celsius and Fahrenheit, both you will put degree. Okay. Now, what is your absolute zero? Absolute zero is minus 273.15 degrees Celsius. This is absolute zero, and the theory says that absolute zero cannot be achieved. Okay. This is absolute zero. Now we talk about what is the lowest temperature so far which has been achieved. So can anybody guess? I remove this from here. What is the lowest temperature the scientists would have achieved? कोई guess करे? What do you think is the lowest temperature has been achieved so far? And we know that 0 Kelvin cannot be achieved. But let me tell you, there are in theories minus temperatures are there, and they can create that. And how do they do it? Some special type of material they develop, and जो टेम्परेचर है वो बेसिकली आपका सिग्निफाई क्या कर रहा है? स्टेट ऑफ द गैस. तो वो उसको फैब्रिकेट करते हैं वो स्टेट को, एंड दैट इज हाउ, एंड that temperature is correlated to negative temperature. So negative temperatures can be achieved. But we are talking in general sense that 0 Kelvin cannot be achieved. So what is the lowest temperature? Let us see. Now there was a person called Owens, and what he did, he liquefied helium in 1908. We're talking about 1908, and the cycle he used was called Hampson-Linde cycle, and he could achieve boiling point of helium at minus 269 degrees Celsius. It is equal to 4.15 Kelvin. This is what he achieved. And further what he did, by reducing the pressure of liquid helium, he achieved an even lower temperature to 1.5 Kelvin. This was achieved in 1908, and he was given Nobel Prize in 1913 for achieving the lowest temperature so far. 1.5 Kelvin. This was 1913. Then there was a person, Stephen Chu. He was an American physicist, and in Stanford University, along with his colleagues, one is Claude Cohen, Tanuji, William Daniel Phillips, they won Nobel Prize in 1997. After about 90 years. Okay. And they did what they did, they cooled sodium atoms to 240 into 10 raised to minus 6 Kelvin. 240 into 10 raised to minus 6 Kelvin. You can see that. But this Nobel Prize was given for the new technique developed to achieve low temperature and not for low temperatures. Although they achieved a lowest temperature so far, but the Nobel Prize was given for the technique they used, and what they did, they cooling and trapping of atoms with laser light. Using laser light, they trapped the material and sodium. They brought temperature up to 240 into 10 minus 6 Kelvin, and it would be about 0.2 millikelvin. Okay. Then there was another experiment in September 2014. There is some collaboration, Cure collaboration, and this laboratory is in Italy. What they did, a copper vessel with a volume of 1 cubic meter to 0.006 Kelvin for 15 days. Now, how this experiment is different from others is that there they produce temperature only for a small quantity, for a small vapors of sodium or a quantity of sodium or helium, and that too for a short duration. But in this experiment, it was a copper vessel of 1 cubic meter, right? If it be iron, 1 cubic meter of iron would be about, I think, how much? 8 tons. That was the big size. Okay. And they achieved the temperature 0.006 Kelvin for 15 days continuous. Okay. So this is what they did. And the lowest world temperature record is 280 into 10 to the minus 9 Kelvin. And there is a laboratory which is called Low Temperature Laboratory in Helsinki, University of Technology, and in 1993 they achieved that. 280 into 10 to the minus 9 Kelvin. And then In 2015, at MIT, they achieved sodium potassium to a temperature of 500 into 10 to the minus 9 Kelvin. So the many people were trying. वो 2014 का है वो, सॉरी नहीं 1993 का है और 2014 का बताया आपको, ठीक है. The record lowest temperature again in Helsinki University of Technology, rhodium metal was cooled to 1 into 10 raised to minus 10 Kelvin, and this was in year 2000. And after that, if they could go still below, we don't know, but it is closest to 0 Kelvin they have got. Okay. So you can see that there are labs which are working only on low temperatures. There are Nobel Prize only for achieving low temperature. Okay. So it has been so important topic in thermodynamics. Now let us talk about 4 temperature scale. How do they look like? These are the 4 temperature scales, and I have put all of them together. If you talk boiling point of water, you have a degree scale here, Kelvin here, Fahrenheit here, or Rankine scale here. The values are given. You can note it out from book also, right? Then the triple point, then the ice point, and absolute zero. Absolute zero is 0 only in Kelvin scale and Rankine scale. For Fahrenheit and degree C, you have to convert it. Okay. So this is how they are related. Now then, how do we convert one temperature scale to another? And you know it. You have been doing converting degree Celsius to Fahrenheit and Fahrenheit to degree Celsius and maybe to Kelvin also. So some brief things, important points to be noted, I would tell you. First thing is that they are all related by an equation y is equal to mx plus c. So you can yourself find out what is m and what is c, and you can find correlation between them. They are all linear scale and interrelated by equation y is equal to mx plus c, right? So on x-axis you can draw one scale, on y-axis you can draw another scale and take 2 points, fill them, right? And you can find what is m and c yourself. Okay, and I have done it here. All this, if you want to convert Rankine into Kelvin, so you multiply Kelvin value by 1.8, you will get value in Rankine. If you want in degree C, you take the value in Kelvin and subtract 273.15 from that, you will get in degree C. Now, okay, and if you want Fahrenheit from Kelvin, you can get this. This is value in Celsius. So if you want to put value in Kelvin, convert it to Celsius, put it here. If you want, if you have direct Celsius value, you can put it here 1.8 into temperature in Celsius plus 32. That will give you Fahrenheit. And another thing important you note that temperature difference in Kelvin and Celsius is same. So 1 Kelvin is equal to 1 degree C. The gradation, the difference between the two is same. Similarly, Rankine and Fahrenheit, their gradation is same. Only thing is Rankine is starting from 0 and Fahrenheit is starting from something minus 457 something like that. Okay. Similarly, Kelvin is starting from 0, Celsius is starting from minus 273.15. But all along The difference remains same. So you can say delta Kelvin is same as delta degree C, delta Rankine is same as delta degree F, and the relation between them is, again you can say, is 1.8. So I think it should be otherwise. Okay. Hmm. Okay. So delta F is smaller and delta Rankine is smaller. So in fact जो डेल्टा K है that is 1.8 times डेल्टा F. तो ये शायद इसको उल्टा लिखना पड़ेगा मुझे. I don't know. I'll check up what is the why I wrote like this. So सेल्सियस का जो ग्रेडेशन है, सॉरी फ़ारेनहाइट का एंड केल्विन का, वो स्मॉलर, सॉरी वो बड़ा है, ठीक है. और जो फ़ारेनहाइट और रैंकाइन का है वो छोटा है. 1 degree Fahrenheit and 1 degree Rankine, they are equal, but they are smaller as compared to 1 Kelvin and 1 degree C. Okay. Now then another point you should, this I have to check up, that is this is actually telling their weight, not the conversion, because for conversion you will have to use those equation y is equal to mx plus c, which I gave just above it. Now then you can say anywhere if delta T is being used, then you can convert from one scale, because if your formula is dependent upon delta T, like heat transfer depends upon delta T. Now if it is talking about delta T, and then instead of Kelvin you can put there Celsius, instead of Fahrenheit you can put there Rankine, because delta of them is same, right? But if there is okay, so whenever you are using thermodynamic relation, if it is temperature difference, then Kelvin can be replaced by degree C without any problem. Similarly, Rankine can be replaced by degree Fahrenheit without problem. And same thing that you the change in Rankine, delta Rankine can be replaced by delta Kelvin, and you have to multiply it, or I think divide by 1.8, thing like that. But when you are using T, not delta T, and capital T in any thermodynamic formula, that is a Kelvin scale, and the value has to be put in Kelvin only. You cannot put degree C, you cannot put Fahrenheit, you cannot put Rankine there. Of course, Rankine you can put, because T is a it signifies absolute. So remember, if you are converting Kelvin into degree C, if the formula depends upon the variation, the difference between the temperature, then you can do it. But if it is not in the it is not depending upon the difference in temperature, but the value of the temperature, then you cannot do it. For example, I give you two equations where you can do it. Suppose I write this equation, Q is equal to minus Ka delta T by delta X. You know this. In this equation, this can be Kelvin or degree C. Your answer will be same, because it is delta T. But take this equation, Q is equal to sigma A T4. This is a radiation. Here T is Kelvin cannot be equal to degree C. You cannot replace Kelvin by degree C. Okay. So this you have to take into account. Otherwise, you will fall into mistake. Okay. So, any questions? Okay, we take one small article here also. Yeah, this much only. Then what are thermodynamic properties? We have talked about it, but some more addition to it. Thermodynamic properties are the properties of a system that change because of the transfer of heat or work between the system and the surrounding. So thermodynamic properties by definition are those properties which changes when heat and work transfer between system and surrounding. Okay, and these are our thermodynamic properties. We already know. Out of these are three are principal thermodynamic properties. We have already discussed it. Principal. Then there is called something state postulate. State postulate is it's a postulate. Okay. So there is no proof for it. The number of properties required to fix the state of the system is given by the state postulate. So if you find that a system is completely defined by two properties, then its state is two-dimensional. There are two independent properties. Remaining all are dependent on that. So it can be different for different system. But they say that for simple compressible system, only two properties are independent. So if you have gases, simple compressible system, only two properties are independent. Which means if you know two properties of a gas out of these 8, then the gas state is fixed. You cannot change the state of gas without changing those two properties. Then how do you find the remaining 6? They are related to the two independent properties. So this is a two-dimensional system or 2-degree system where the remaining 6 are dependent on the 2. And how do you find what are those equations? One is the equation of state. PV is equal to nRT. Here you will find volume is dependent on pressure and temperature. So pressure is independent, temperature is independent. If pressure and temperature are given, volume is known. Okay. So third property is clear. The fourth one comes from this. Enthalpy is equal to U plus PV. If you know U, internal energy, and PV, we already know P, T and V. Okay. So that means we know PV. So if we know U, H is also known. That means U and H are related. From U you can find H, from H you can find U. Okay. Then there are 4 thermodynamic relations known as Maxwell equations. So you have total 6 equations to determine all the other 6 properties. These Maxwell equations we will be studying in the end. And Maxwell equations are actually, you can say, using the first law and second law and applying them to these gas system. Okay. So जो मैक्सवेल इक्वेशन है उससे हमारे रिलेशन आ जाते हैं और हम बाकी प्रॉपर्टीज को निकाल सकते हैं. So this is what happens. ठीक है. So we will stop here and Now we will start 0th law of thermodynamics. So that we will take up next class. This is also an interesting law, and unfortunately people even in the highest educational institution do not know what it is. मेरी कई सीनियर प्रोफेसर से इस पे डिस्कशन हो चुका है. अब द प्रॉब्लम इज कि जो चीज यूज नहीं होती, बिकॉज जीरो लॉ ऑफ थर्मोडायनेमिक्स इस आर्टिकल के बाद कहीं यूज नहीं होगा. इट इज नेवर यूज्ड इन एनी न्यूमेरिकल, it is never used in any problem. You have just one article on zero law of thermodynamics and it's over. So the people ignore it. They just take it as ठीक है, इसकी तो कोई जरूरत ही नहीं है. But it's a very fundamental law. It's a very, we will discuss about it. बड़ी interesting है ये law. और इसकी necessity क्या है? Why it has come? तो बट आई वॉज इंटरेस्टेड इन इट, सो मैंने कहा कि इसको देखें क्या होता है. जब मैंने पढ़ के देखा तो समझ में आया कि ये जो है दिस इज समथिंग वेरी इंपॉर्टेंट. ये कुछ ऐसा है कि जब आप थर्मोडायनेमिक्स को मैथमेटिकली अप्लाई करना शुरू करते हो, तो मैथमेटिक्स में क्या होता है, देयर आर imaginary cases are also possible. Physics goes by reality. Mathematics takes both reality and imaginary. तो जब आप उसको फिजिक्स को मैथमेटिक्स में ट्रांसलेट करते हैं तो 1-to-1 ट्रांसलेशन नहीं होता है. Because if you have not taken care of the difference between the two, what will happen? Mathematics, because you will use mathematics, you will go by mathematics. Mathematics will put you in such situation where you will find कि ये तो हो ही नहीं सकता, क्योंकि मैथमेटिक्स जो है जो इमेजिनरी पॉसिबिलिटीज है उनको भी ले आती है, और जब वो आ जाती हैं तो आपका जो रिलेशन है, अगर आपने इफ यू आर गोइंग अलोंग विद द सॉल्यूशन, तब तो आप बीच में चेक कर लोगे. बट व्हेन इट इज डूइंग ऑटोमेटेड बाय कंप्यूटर्स, ठीक है, तो क्या होगा कि आप कहीं जगह ऐसी जगह में पहुंच जाएंगे जो कि इमेजिनरी होगी या गलत होगी, एंड देन यू विल बी सरप्राइज कि ऐसा क्यों होता है. एंड बिकॉज यू हैव नॉट फॉलोड द कैलकुलेशन, यू डोंट नो व्हाई इट हैज हैपेंड, एंड यू विल बी वॉदरिंग कि ये रिजल्ट गलत कैसे आ गया. जैसे फॉर एग्जाम्पल यू वुड हैव डन द प्रोग्रामिंग. प्रोग्रामिंग में एक चीज हम हमेशा डालते हैं, डिवीजन बाय जीरो इज लेफ्ट आउट. कहीं भी डिवीजन बाय जीरो होगा तो उसको हम रोक लेते हैं, उसको सेग्रीगेट कर देते हैं. व्हाई? Because if you don't allow that, if you don't do that, your results will come wrong. Same thing when you have square root, you put the condition that the इसका जो वो है term है वो that should not be negative. If that is negative, you are gone. Either your program will stop or it will create some fictitious solution. तो इसी तरीके से देर इज ए प्रॉब्लम हियर ऑल्सो दैट वी हैव टू एड्रेस. जो मैथमेटिकल सिमिलैरिटी की प्रॉब्लम है जिसको हमें एड्रेस करना पड़ता है, ठीक है. और पीपल टेक इट वेरी लाइटली कि नहीं ये कुछ नहीं है, ए इक्वल टू बी इज इक्वल टू सी. तो इफ ए इज इक्वल टू बी एंड ए इज इक्वल टू सी, देन बी इक्वल टू सी. ये हो गया फर्स्ट लॉ. सेकंड, 0th लॉ. इट्स नॉट दैट, ठीक है. तो एनीवे, विल स्टॉप हियर.